Hello, everybody. Good morning, good afternoon, good evening from wherever you may be joining us from today. I'm Mark Ogg, Chapter President for CSINext for 22 and 23. Welcome to our June chapter meeting where we are going to learn about electronic leak detection for roofing, waterproofing, and the building envelope with Shaun Katz from DTech Systems. Before we get started and I turn it over to Shaun, just wanted to cover a little bit of chapter business. This will be our last meeting for the 22-23 fiscal year. The new year will start up in September, and your chapter board is hard at work in getting everything planned for next fiscal year's activities and chapter meetings. If you have any ideas or thoughts or would like to be a presenter at one of our monthly meetings, please reach out to anybody there on the chapter board at the CSINext website, or send an email to info at CSINext.org, and we will be happy to get back with you and discuss your topic or your questions. Before we get going here, I just would like to put in another huge thanks to all our chapter sponsors for this year. Architectural Woodwork Institute, National Gypsum, Northern Facades, KM Architectural Consultants, Avis, and Daniel Hargreaves. Without the continued support of you fine folks and your involvement in the chapter, none of what we have been able to accomplish so far would be possible. And this has been a great year for CSINext. We are over 122 members worldwide. And that is the largest I've ever seen a chapter as I've been involved in it. And it is continuing to grow, and we're adding members every. It's been a great experience. Our website is doing well. We have the blogs, we have member interactions. It's just been a great year for us, and looking forward to continuing that next year and beyond. So at this juncture, I will turn it over to Shaun, let him introduce himself and take us through his program today. Shaun, it's all yours.
Thanks, Mark. Appreciate everybody taking the time out of your day to join this presentation. Again, my name is Shaun Katz. I'm the product line manager for DTech Systems. We're just a small electrical engineering firm that has invented leak detection testing and monitoring technologies for roofing and waterproofing. So this presentation is entitled Electronic Leak Detection for Roofing, Waterproofing, and the Building Envelope. And it is worth one AI learning unit. It's also worth one IBEC credit. So please send, if you are an AIA member or an IBEC member, or you would like a certificate of today's or a certificate of completion, please reach out to Mark with your information, and then we can report attendance to AIA and send that certificate. So this presentation covers the physics of electronic leak detection. I'll discuss the 4 different methods that are found in the ASTM standards. Then I'll tell you about valid leak detection assemblies, and then which ones need what's called a conductive medium. That's something that gets added into a roof assembly to make ELD work when it's needed. Then I'll tell you about fully monitored systems, and we'll finish off with case studies. If you have any questions at any time, you can send them in through the chat or the Q&A, and they will be addressed at the end of the presentation. So electronic leak detection, that is the current generic term that is used for the 4 different methods that pinpoint breaches, holes, and seam voids in roofing and waterproofing membranes. And they're all typically used as a quality control test in new construction. And the whole purpose of ELD is to provide risk mitigation and loss control. And it's doing that by pinpointing the breaches in the membrane before the roofing warranty starts or before overburden is installed. It works by applying an electrical current to the surface of a membrane. The current flows through a breach or a hole. It touches the conductive substrate under the membrane, which then carries that electrical current back to where the equipment's connected. So this is a typical waterproofing assembly where we see a membrane installed directly onto structural concrete. Structural concrete is conductive already. Those dashes on the right-hand side, that's where the equipment gets connected to building ground. So a grounded object, like a metal drain. So the equipment gets connected to a metallic object. The equipment applies the current to the surface of the membrane. Current flows through a hole, touches the concrete, and that current flows through the concrete back to the metallic penetration. So that is the physics of ELD in a waterproofing assembly. Now, in a conventional roof, there's usually coverboard, insulation, and a vapor barrier or retarder that's between the membrane and the conductive deck. And because of that, the electrical current is broken. It's disrupted. Therefore, ELD testing is not possible with reliable results unless you add in what's called a conductive medium. And that's what you're seeing in this image. So a conductive medium gets installed into the assembly directly below the membrane, and that creates that required conductivity for testing to work. These dashes over here, this is where the equipment gets connected to a grounded object. So again, the equipment applies the current to the membrane, flows through the hole, touches the conductive medium, which is carrying the current back to where the equipment's connected. So that is the physics of ELD in a brand new conventional roof. Now, ELD has 4 basic requirements. This is for all 4 methods. They all require a conductive substrate directly under the membrane. That's either going to be structural, concrete, metal, or some type of conductive medium. And I will touch upon that here shortly. They all require a ground connection to that substrate. So any metallic object connected to the substrate and penetrating the membrane. So think metal drains, lightning rods, HVAC units, conduit, rebar, term bars. The membrane has to be exposed, meaning it cannot be covered by overburden, pavers, topping slabs, vegetation. It's one of the biggest exaggerated claims in the industry, and I will touch upon that here shortly as well. And the membrane's got to be clean of trash and staged materials. This is not a condition that a technician wants to test in. This would be considered invalid testing unless they clean up that area. And then all 4 ELD methods require an electrical path from the surface of the membrane to the surface of the conductive substrate under the membrane. There's 2 types of ELD, high voltage and low voltage. High voltage is a dry test, and you can actually see that spark travel through air. On the right-hand side, that is for low voltage testing. Low voltage testing uses water, and wherever that water flows, the electrical current will flow. These are the 2 ASTM standards for ELD. The first came out in 2014. That is the ASTM Standard Guide D7877, and it lists the 4 different ELD methods. That includes the low voltage scanning platform, low voltage vector mapping, the low voltage vertical roller, and then there's high voltage. It's also called spark testing or holiday testing. So the 7877, it lists those 4 methods, describes the testing apparatus that's being used, the testing procedures, and the limitations of each test. But other than that, they all have the same physics and requirements. Exposed membrane, conductive substrate, completion of an electrical circuit through a hole, same physics. Now, after 2014, ASTM asked that each method create their own standard practice. You all know there is a difference between a guideline and a practice. And so in 2019, the very first standard practice was created, and that is the ASTM D8231. It is specific to 2 of the 4 methods. The other methods have not created their own practice yet. It does expand on that 7877, but it also reflects all the technical advancements in ELD after 2014. So for example, when the 7877 was published, no one had the ability to test a semiconductive membrane like black EPDM. And then in 2017, the scanning platform method was modified so it could drown out the conductivity of a membrane and be able to find that hole. And so that new ability in ELD is reflected in this D8231. So this is the first method I'll tell you about. It's called high voltage. It's also called spark testing or holiday testing. And this method was created in Europe in the 1960s. And it was originally created for testing coatings on pipes. And then the technology was adapted for roofing and waterproofing. This one works on horizontals, verticals, transitions, details, but only works on a non-conductive membrane. It doesn't work on something like black EPDM. There's also some cold fluid applied coatings that are semi-conductive. You could tell which ones those are if they contain carbon black, have metallic flakes, or a high moisture content. All that makes them semiconductive. So this works on non-conductive surfaces. The technician either uses a broom or a brush apparatus, and they apply up to 40,000 volts to the surface of a completely dry membrane. And at the location of a breach, there's going to be a spark. And they can hear a pop. So here's a short video. That is a high voltage ELD test. You do not want to touch that spark. Trust me, it hurts. So these are the limitations of high voltage. The most well-known is that this can only be performed in dry conditions. It's rarely seen here in the Pacific Northwest where I'm located. You cannot perform this in inclement weather. There cannot be frost or dew or any pooled water on the surface of the membrane. The equipment will spark into that moisture thinking it's a hole. So the surface of the membrane has to be dry. And the technician has to adjust the voltage for the mill thickness that they're testing. And so in a fluid applied application, if that thickness fluctuates, and if the voltage is set too low, it might not spark. And if the voltage is set too high, it might actually burn through the membrane and create what's called a holiday. This one is also not the best for seam void detection. That is because the spark only travels vertically through a direct vertical air gap. It does not bend or travel horizontally. So this requires a vertical air gap to spark. So seam void detection isn't the best with this method. As you all know, seams are overlapping, and this would only spark if there's a vertical air gap to the conductive substrate. The next method I'll tell you about is called low voltage vector mapping. This was also created in Europe in the 1970s, and this was originally created for testing pond liners that were filled with water. Then the technology was adapted for roofing and waterproofing. This one works on horizontal surfaces that are not conductive. It doesn't work on black EPDM or those semiconductive cold fluid coatings. The technician will set up a wire on the surface of the membrane. You can see it right there in the background. All that wire does is it isolates the testing area, usually up to 7,000 square feet or less. And then within that wire, all grounded objects have to be isolated. That's because these are going to be seen as a hole or a breach in the membrane. So they have to be isolated from the area. And low voltage ELD flows through water. It does not jump through air. So the larger the area that gets isolated, the more water you need in a continuous path within that perimeter wire to carry the current. So if that area is sloped, or there's drains or dry spots or gaps in that water coverage, the electrical current can get broken or disrupted. So best practice with this method is to flood the membrane with at least 1/4 inch of water or more. Typically that doesn't happen. Sometimes it's just not feasible. So what you might hear is the addition of dish soap. Dish soap mixed with water helps to create a continuous film without flooding it. That's what you're seeing in this image. So again, the larger the area that gets isolated, the more water you need in a continuous path to carry that current. Gaps in that water coverage means breaches can be missed. So technician sets up the wire to isolate the area, then they isolate all the grounded objects, then they flood the membrane with water, and then they use these probes. There's a couple of different methods. Some look like ski poles. Others look like head scratchers. They're all the same type of technology. It's just a different looking apparatus. So isolate the area, isolate the grounded object, flood the membrane, and then they apply these probes to the surface of the membrane. And the electronics point the technician in every direction where it reads 0 volts. So basically what's happening here is that wire that they set up to isolate the area is pulsed with up to 40 volts of electricity. The surface of the membrane where there's water is around 40 volts. The location of the hole or the breach is 0 volts or building ground. So when those probes hit that wet surface, it's pointing the technician in every direction where it reads 0. And that can be a complete nightmare for technicians if there's a lot of breaches or pinholes or it's a large area. So the technician will pick a direction. They start walking in that direction, poking the surface of the membrane. And when they get close to 0 volts, that indicates where there's a breach. When that breach is found, it has to be repaired right then and there or isolated from the area, because this sees the sum of the entire area at one time. So as breaches get found, if they don't repair it or isolate it, the equipment will continue to see it throughout that test. Also, this is pointing in a direction of a drop in voltage. So if you have multiple breaches that are close in proximity, it's still pointing in that direction, but they might be too close to differentiate where they are. So breaches near each other can get missed with this method. Here is a short video of the vector mapping ELD test. So there's the wire, there's the flooded water path, these are the probes. Now, most ELD testing agencies that use this method don't use it on a vertical surface. It can be done within its limitations, it's just not really feasible. The equipment manufacturer in the United Kingdom, they will tell you, do not use this method on a vertical surface. But again, within its limitations, it might be possible. Those limitations are, the wire has to be set up on a vertical wall. One extra body will stand there spraying water. The water has to hit the wire, which is pulsed with 40 volts. The water must flow in a continuous path, make its way through the hole and touch the conductive surface below. So while it's possible, it's just not feasible. And most ELD testing agencies either use high voltage or the roller apparatus for a vertical surface, not this method. So there's that wire, that perimeter wire. And again, the wire just isolates the testing area. The problem is it's usually set up 2 to 6 inches from a vertical wall, which means this method can't test transitions. And all grounded objects, like drains, have to be isolated. You all know these are actually some of the most common areas where a breach or a hole is found in a membrane. Now, this is actually one of the most exaggerated claims in the industry, the ability to reliably test through overburden. Now, this is the only method out of the 4 that can work in limited situations. Think soil or gravel installed directly on top of a membrane with nothing in between it. Because in that case, the tips of the probes can penetrate those materials and touch the membrane itself. Still needs the wire to isolate the area, and the membrane has to be flooded with water. So within those limitations, it might be possible. But if electrically insulating materials are added above the membrane, it's blocking the circuit. The only way to bridge that gap is with water saturation from the top down. So the further you separate the equipment from the membrane, the more water you need from the top down. So in an extensive or an intensive overburden situation, here's the only way it could possibly even work. That substrate directly under the membrane has to be conductive. Usually it's structural concrete. The membrane itself has to be non-conductive. So it cannot be black EPDM or any membrane containing carbon black. Now, we actually found through R&D that some membranes like hot fluid and SBS mod bit, when they're sufficiently saturated with water, over time, they become semiconductive, which means if that happens, and if this equipment is able to read through all these layers, it cannot sense the difference between a breach or a conductive membrane. The equipment would be an alarm, it's a false positive. So that is possible if the membrane becomes conductive over time. The wire has to be left in place. Now, when that technician leaves site, they disconnect from the wire, they leave site. It could be days, weeks, months before overburden gets installed. You might have other trades walking through that area, dropping their tools, dragging their equipment, damaging that left in place cable, moving it, disconnecting it. There is no way for a technician to know in the future, standing on the surface of the overburden, there's no way to know the placement or condition of that left in place cable. And that entire test is dependent on it. So it has to be left where it was and in the condition it was in the initial test. Keep in mind, this method can't test transitions, details around grounded objects or vertical surfaces. So you could have holes in the membrane that just were never even found in the initial test due to limitations of this method. The membrane has to be flooded with water. That's what's carrying the electrical current. Gaps in that water coverage means breaches will get missed. Tell me, how does a technician know in the future, standing on the surface of the overburden, how do they know how much water is physically standing on the membrane? That entire test is dependent on it. It's got to be flooded. Then there has to be a continuous, unbroken water path from the surface of the overburden where the probes are through all those layers, coming in contact with a completely flooded membrane. That water path from the top of the overburden down can also not be confirmed. So, could this be used as a troubleshooting feature? Possibly. Is it valid or reliable? Absolutely not. The equipment manufacturer in the United Kingdom will tell you they have never even seen a test through overburden. They've tried repeatedly internally to get reliable, repeatable results, and they've been incapable of doing it. The problem is you have testing agencies that purchase the equipment. They sell left in place wire with future testing through overburden without explaining the physics and the requirements. And they're selling invalid testing actively. So there is no known technology in the industry that can reliably test through any kind of overburden. Valid ELD is only on an exposed membrane. It is the same problem with the split slab. Now, that topping slab is conductive. So the moment the probes hit that surface, it's going to be an alarm. Even if it could read through these layers, you all now know the physics of low voltage ELD. What is needed from the top down to complete the circuit? Water. It would have to be flooded. We all know that's not going to happen. Same problem with pavers on pedestals. Remember, low voltage ELD flows through water. It doesn't jump through air. So if the wire is to remain in place and they hope to test through these layers, what is needed from the top down to complete the circuit? It would have to be flooded from the surface of those pavers down. And we all know that's not going to happen. So these are the limitations of vector mapping. The most well-known is that it has a lengthy setup process. You have to isolate the testing area, isolate all the grounded objects. You got to flood the membrane. It cannot test transitions, details, and verticals, and it cannot test a semiconductive membrane. Now, 30 years after those methods were created, two new ELD methods came along. That's the low voltage scanning platform and the low voltage vertical roller. And these two units come as a package. And they were created to simplify ELD, to make it more user-friendly, to take out some of the requirements and limitations. So it's got the speed and ease like high voltage, the ability to test horizontals and verticals all like high voltage, but this is a low voltage method. So again, low voltage ELD has a water path from the top down. This is the scanning platform. This is designed for testing horizontal surfaces only, but this is the only one out of the four that can test nearly every single type of membrane in the world, including semiconductive membranes like black EPDM. It's similar to vector mapping. Remember, vector mapping isolates the area with a perimeter wire. This unit has an isolation area built in, same type of requirement. And the center chain is what's actually searching for the breach. So it doesn't even sense that void until it's directly below the platform. Now here's a short video, but before I hit play, look at the water. This is what I was trying to explain about a gap in water coverage. That's why with vector mapping, the larger the area that gets isolated, the more water you need in a continuous path to create that circuit. You can see here on new membranes, water pools, it beads. and that's a break in the electrical current. Now, this unit has a built-in feature to where the technician can place their hand on what's called a secondary sensor bolt. What that bolt is doing is that's passing the 9 volts from the electronics through the human body, which is conductive, and out the hand. So the body can be used to complete an electrical circuit. That's how breaches get pinpointed, or how testing is done around a very difficult to reach area or tight space, or around something like a drain. So if you're seeing that image on the right-hand side and you remember the other methods, remember high voltage sparks if there's a vertical air gap. Vector mapping would isolate the drain from the area. This unit carries the current as close to that drain as possible. It's also how testing is done around the flashings around a grounded object like rebar. So here's another video showing how the hand is completing a circuit around these flashings. So that is a low voltage test using the hand. The final ELD method is called the low voltage vertical roller. This one is designed for testing verticals, transitions, details, horizontals, but only works on a non-conductive surface. This does not work on something like black EPDM. The technician saturates that roller in a bucket of water, presses it against the membrane, drags it up that vertical surface, pushing the water into the membrane. And at the location of the breach, the electronics will squeal. So here's another video showing how the roller pinpoints a breach in a transition. So that is the low voltage roller. So again, these 2 units were created to simplify the process and to make it more user-friendly. The platform works on horizontal surfaces, and that surface has to be wet. The roller has to be saturated with water. Wherever that roller goes, the current flows. And the roller does not work on semiconductor membranes like black EPDM. Now, with that being said, the technology has been created. That is the next technical advancement in ELD, vertical conductive membrane testing, and it should be coming out by next year. Now, here are all 4 ELD methods compared. They can all test an inverted waterproofing assembly. They can all test a brand new conventional roof with an added conductive medium. I'll get to that here in a moment. High voltage is the only unit that works in dry conditions, and low voltage are the only methods that work in wet conditions. They can all pinpoint a breach. They can all test horizontal surfaces. High voltage and the roller are the only 2 units that can reliably test a vertical surface. Vector mapping is the slowest out of the 4. It's the only one that needs to isolate the testing area and all grounded objects before testing is performed. Seam void detection is best with low voltage ELD. Again, wherever water flows, the electrical current will flow. The platform is the only method out of the 4 that can work on both non-conductive and semiconductor membranes like black EPDM. And as of August last year, Factory Mutual, or FM, just created a whole new roof leak detection classification. It is the FM approvals 7745. But basically what that means is any FM insured building that requires ELD can only use the FM approved ELD methods, and that is the platform and the roller. Those have been tested internally by the electrical team at FM. So here's a quick spec tip. Typically, you're going to find this scope in Division 7 in the field quality control section, all the way at the end of the spec in field quality control. And there's been a lot of different terms used over the last 50 years. It creates a lot of confusion for bidders using all those different terms. So you might see things like vector testing, EFVM, HVIT, membrane integrity survey, breach detection. It's all referring to the same thing. So if you're a spec writer, you should be using the most current language. That term is electronic leak detection. It encompasses those 4 methods. I'd also suggest referencing those ASTM standards because that's what holds your testing agency accountable. There are numerous testing agencies out there that make claims that are in conflict of what those ASTM standards state. I'd also suggest you including your spec when you want testing to be done. Testing should not be performed if the membrane is going to sit exposed to other trades or weather over time. So it really should be done at the very last possible moment, just prior to covering with overburden or just prior to starting a roofing warranty. If it is a conventional roof like TPO, PVC, EPDM, ModBit, then almost always it's going to need what's called a conductive medium. And that's just a specially designed product that gets added into the roof assembly directly under the membrane, and that creates that required conductivity for testing. It's one of the most commonly missed items that doesn't get specified for roofing, and it leads to either deleting the scope or invalid testing. If it's a semiconductive membrane like black EPDM, your specs should read slightly different. You don't want to reference all methods since they all don't work. And you don't want to reference the 7877 as that was published before the ability to test black EPDM was invented. So your language would be slightly different. And if it is an FM insured building, that limits which testing methods can be used. Now, typically, ELD is used as a quality control test in new construction. It can be used to locate an active leak. We call it forensic ELD. The physics are the same: conductive substrate, exposed membrane, electrical path from the top down, and that path is carried through water. And the further that water has to travel, and the more layers it needs to travel through, the harder it is to find a breach in a membrane. But if you've got water already coming into the building, well, then at that point, we know water's touching concrete or metal. We just don't know where it's coming from. Was it trapped at the vapor barrier in construction? Is it coming from a vertical surface? Is it coming from a drain or a penetration? Or is it coming from a hole in the membrane? If it is a hole in the membrane, each hole needs that path from the top down for it to be found. So it might take a couple of forensic ELD tests to be able to find all those breaches. Back to new construction. All 4 ELD methods require a conductive substrate directly under the membrane. On the waterproofing side, that's usually structural concrete. These are the 4 non-conductive or electrically insulating substrates. Typically, it's coverboard. It could be insulation. Wood is not conductive. Lightweight concrete or lightweight insulating concrete might not be conductive enough. So if the membrane is already installed and it's new construction and there's no active leak, it's new construction, membranes installed already on any of these 4, you could perform ELD, just the likelihood of finding anything is extremely slim. That's because these substrates can't carry the circuit unless that water saturation is touching something grounded. If the membrane has not been installed yet, then there's the ability to add in what's called a conductive medium. Again, that's a specially designed product, gets added into the assembly directly under the membrane, and there's the required conductivity for testing. So these are your options. There's what's called the conductive primer. This is a water-based primer with carbon black. That's what makes it conductive. Contractor mixes a pail, paints it onto the surface of the substrate, it dries, then they put down adhesives, primers, and then the membrane. This one's UL listed. It is the only one that is FM approved. It's listed in over 10,000 assemblies currently. It is the only one in DORA, and it's the only one approved by the Florida Building Code. This one, you can adhere to it. You can torch directly to it. It does not catch fire. You can fasten through it. It has approvals with fluid applied coatings and loosely laid membranes. So out of the 3 conductive mediums, this one is the most widely accepted, tested, and approved for placement directly under the membrane, which is where it's needed. Then there's what's called the fleece. Sometimes it's called a felt. This can create issues with adhesion, so you're typically only going to find this in mechanically fastened or loosely laid assemblies with overburden. Then there's what's called the mesh. Sometimes this is called a grid. It could be aluminum. It might be stainless steel. It's just chicken wire that you find at a hardware store. The problem is it creates issues with adhesion. It punctures membranes. And so because of that, a lot of the manufacturers force this one to go below the cover board. Now, this is addressed twice in the ASTM standard. It states in section 4.4 and 5.5 that when the substrate under the membrane is non-conductive, the path to building ground is broken. It's disrupted. And the only way to remedy that situation is by adding in a conductive material directly under the membrane, and that creates the required conductivity for testing to work. So while placement below the cover board is better than nothing at all, again, the whole purpose of adding in a conductive medium is to create a valid, reliable, quality controlled test. If this is placed below the cover board, what is needed from the top down to complete the circuit? Water saturation. And that defeats the whole purpose. That would create moisture intrusion into the assembly, and you cannot confirm that every breach that's present has that water saturation. So proper placement is directly below a membrane.
Hey, Shaun, got a
Yes.
quick question here. If the testing requires water or water saturation, how is the installed assembly protected from damage during testing and from extended water damage after testing?
So, so for the physics of ELD, in this case, okay, if you've got a conductive substrate directly below the membrane, it's only a path from the top down. In this case, with the improperly placed conductive medium, this type of testing should not even be sold. Not only is it an invalid test, but it requires that moisture saturation and intrusion for the test to even work. It's not suggested. So that's for new construction projects, not active leak forensic. I'm about to get to that here in a minute.
Okay, thanks.
Does that answer your question, Mark?
I believe so. If not, I'm sure somebody will ask another one.
Sounds good. So let's see here. Here's a quick spec tip for conductive mediums. Typically, conductive mediums are only needed in conventional roofing. So TPO, PVC, EPDM, mod bit, or any situation where the membrane is going directly to something non-conductive. Usually that's coverboard, might be insulation, could be wood or lightweight concrete. The spec needs to be very clear about where the conductive medium needs to go. That word directly is extremely important. That's what's found in the ASTM standards. That is the science and the physics of ELD. You will find that some testing agencies that sell conductive mediums, they leave that word out. They'll state, place conductive medium below the membrane. Generic enough to where if it goes below the cover board, it met their recommendation, does not mean it meets the ASTM standards, doesn't mean it's a valid test, but that's where it'll be allowed. That is an invalid test, should never be sold unless everybody knows up front testing results are invalid and inconclusive. I'd also suggest referencing the ASTM standards in your spec. That's what holds your testing agency accountable. Again, there are testing agencies that actively sell invalid testing without explaining physics, requirements, limitations. It's a big problem. Take it one step further. State placement of a conductive medium is only allowed directly below the membrane. Again, the whole purpose of specifying this is to enable valid, reliable quality control test. That is the science and the physics, and that's what the ASTM standards state. I would suggest that the spec tells the contractor, hey, before you submit your quote, make sure that whatever conductive medium you're quoting is approved by the membrane manufacturer. And if it is an FM insured building, that limits which testing method can be used. It also limits which conductive medium can be used, which is only the primer, and it limits which membrane manufacturers can be used. That's all found in FM approvals 7745. Now, there are fully monitored systems available as well. You've got systems for inverted waterproofing as well as conventional roofs. On an inverted waterproofing assembly, it works just like ELD. The substrate directly under the membrane has to be concrete or conductive. The membrane has to be non-conductive. ELD testing is performed on this membrane first. Breaches get found, repaired, and then retested. There's your baseline reading of the area. It's found to be free of holes. Immediately after that, sensors need to be installed in a grid-like pattern to isolate the membrane into zones. Immediately after that, the area has to be covered up by something like drain mat. That is to protect the membrane and those sensors from damage. If you leave those areas exposed, it's highly likely the trades will come in, damage the membrane, trip over those sensors, rip up the cables, and all that work has to be repeated. So test the membrane, find the holes, repair those holes, retest the repairs, install the sensors, cover it up immediately. Over time, water makes its way through the assembly, hits this waterproofing layer, and the water will travel. The system charges that water with a low voltage electrical current, taking data over time of how that current flows in each zone. So if you have a hole, water flows through the hole, touches the concrete, completing an electrical circuit, just like ELD. Yes.
On the breach detection, it is 24/7 continuously monitored. Does it report back to its own monitoring system? Like, will you have your own type of alarm or something, or can it be?
Yep.
Can it be tied in? Like, I know mechanical systems get tied into a lot of things via BACnet.
Yep. Both.
These days, it can do both. Great.
Yeah.
Okay.
So basically, it's typically always connected to a cloud-based monitoring center. That's where the data is held. There are some customers that want what's called a self-contained system where there's no outbound data. And basically you just put a computer on site with the software, but it's all handled in-house. You can also connect it to BMS systems, BACnet, all of that. Absolutely. Now, this is the system for conventional roofs. It's a moisture detection system. In this type of assembly, the sensors go down on the lowest layer where water can travel horizontally. That's usually the vapor barrier. And so the sensors go down in a grid-like pattern on the surface of the vapor barrier ahead of the roofing contractor. At the end of each day, they seal off the work that they've done. These sensors get activated and they start monitoring for trapped moisture the day of construction. And I can tell every single one of you that pretty much every single conventional roof in a wet climate is most likely going to have some type of moisture intrusion at the vapor barrier starting in construction. And I will show you that here shortly, almost every single time. Now, the system indicates where moisture is hitting the vapor barrier, tracks where the moisture moves. It provides the time frame, but it doesn't pinpoint the source in the membrane. It'll give us an area of where the moisture is coming from because we know the water is going to travel vertically. So we'll have an area of where it's coming from. But to pinpoint the source, you still need a conductive medium so ELD can pinpoint the hole in the membrane. It works together in this type of assembly, and this is all found in FM approval 7745. This system is also FM approved. There are adaptations. You can basically place moisture detection sensors anywhere where trapped hidden moisture is of concern. So think beneath windows, mechanical room floors, interstitial spaces within walls, ceilings. The image on the left-hand side, that was a pool built above a very expensive apartment, so sensors went on the ceiling. The image on the right, that was an underground research facility built next to a lake, and they were concerned water would make its way through the walls, so that's where the sensors went. The system can go anywhere where trapped hidden moisture might be of concern. Now, one of the major advancements of the moisture detection system was the ability to start pulling that data in construction. These systems need power and data. Usually the sensors would go down, but power and data wouldn't be in the building for 6 months to a year. The system would get plugged in and the vapor barrier would read wet. Every single project, everywhere in the entire world. Nobody could tell when or where the moisture intrusion began, but what could be confirmed is that there's always standing water on the vapor barrier. So what was decided was that the data needed to be pulled in real time. And to do that, the electronics got mounted in a weatherproof case with a battery backup and a cellular gateway. That enabled the ability to pull the data in real time, which confirmed our suspicions that pretty much every single roof in a wet climate is going to have some type of moisture intrusion during construction. It could be due to installing wet staged materials. We see that here in the Pacific Northwest. Could be due to roofing in the rain or in the winter time. We've seen it here. It could be due to night seal failures. That's what you're seeing in the image below. So basically the contractor seals off the work that they've done that day. A rain event occurs, that seal fails, and it floods the assembly. We've seen that dozens and dozens and dozens of times. And then it's the other trades. They come in, they walk around with the nail in their boot, they're dropping their tools, they're cutting into the membrane, they're welding, and it's creating voids, and that leads to moisture intrusion. We have seen options for moisture removal. We have seen contractors pump water out, and we've seen others force air in. And that drying out process is all part of the monitoring center. So you can see here, systems reading dry. Once water hits the system, goes into full-blown alert. And this is actually the drying out process. And there are smart drawings. Green is dry, orange is damp, and red is wet. Just a couple of case studies. This is a light rail station in Seattle, Washington. And this is a rapid curing cold fluid applied coating, which is extremely prone to pinholes. Every year, I track how many square feet is tested and how many breaches are found. And I track by manufacturer, by membrane type, if it's new construction, forensic. Every year, I've been tracking that information. And every year, the average is always about the same. 1 breach for every 500 square feet tested. This membrane, last year's average was 1 breach for every 200 square feet tested. So this membrane is extremely prone to pinholes. Pinholes is something that we commonly find in cold fluid applied coatings as well as traffic coatings and polyureas. And often ELD gets deleted out for something like a flood test. Well, a flood test can take a whole day just to build the dam. Then they flood it for 1 to 3 days. It cannot pinpoint breaches, cannot tell you how many breaches you have, and it cannot test a vertical surface. ELD, on the other hand, can pinpoint every single hole in that membrane, can test anywhere between 20 and 40,000 square feet in 8 hours, and any breaches found can be repaired and retested that same day. So I highly suggest keep ELD in rather than something like a flood test. This is a case study of a mixed-use building in Redmond, Washington. And on this job, this was a membrane installed directly onto coverboard. No conductive medium was added in. Warranty began, eventually began to leak. And the roofer went to site repeatedly trying to find the source, and they were unable to. So they asked for ELD testing. And they were instructed to wet down that membrane for 3 days leading up to the test. It's already leaking. So we know it's touching concrete or metal. We just don't know where it's coming from. So 78 breaches, holes, and seam voids were found. They were all repaired and retested that same day. We found that all it takes is an improper seam weld with just a few fibers hanging out, that is enough to wick the water into the assembly. If they had added in a conductive medium, that would have enabled the ability to test in new construction as well as for the life of the building, and the electrical path would only have to flow from the membrane of the coverboard below. In this case, 78 breaches with water saturation all the way down to the deck. Those breaches were repaired, trapping all that water in. Now, what we don't know is how much was trapped at the vapor barrier starting in construction. I'm going to show you that now. This is an apartment building.
Got a quick question on that light rail station. What are the typical causes of the pinholes on an application like that? Is it
We don't
high
determine.
heels, canes?
We do not determine the cause. For leak detection testing agencies, they're there to perform a test as QC to find the holes. How those holes got created is above and beyond testing agency's scope.
Okay.
Could
So it
be,
could be really from anything.
yeah, it could be from anything. The ELD testing is just a quality control test to find those holes. How those holes got there isn't up to the tester. You know, they can investigate it, but for us, it's just repair those holes, retest it. Is it good to go?
Okay, thank you.
Good question, though. Now, this is an apartment building in Portland, and it had 2 green roofs. And this is the project where monitoring during construction was developed. So again, leading up to this job, sensors would go down, but it wasn't pulling any data until there's power and data in the building. And by then it was too late. So this is the project where the data was pulled in real time. It was Thanksgiving weekend, and the project manager received an email that one zone had gone into alert. 15 minutes later, the system pulls another set of data. 2 additional zones went into alert. 15 minutes later, another zone. After that long weekend, contractor showed up on site, cut into the assembly, and there was standing water on the vapor barrier. The system indicated the source began around this HVAC unit, and there was a time frame. Someone had shown up on site, cut a curb around the HVAC, didn't tell anybody. It rained over a long holiday weekend. The water saturated down, hit this zone, and then traveled to 3 additional zones within 45 minutes. These zones were 20 feet by 20 feet long. That is how far and fast water travels when it hits the vapor barrier, and no one would have known if it hadn't have been for a monitored system. Final case study is a medical technology manufacturer in Minnesota. You see here that they required the monitored system. They did not add in a conductive medium. Therefore, they cannot perform ELD on that membrane. Again, it works together in this type of assembly. Sensors are monitoring for moisture. Conductive medium enables ELD. ELD pinpoints the holes. This is the center of a 15-foot by 15-foot grid. Wiring gets connected to the center of each grid, comes back to a central location that houses the electronics. Those electronics pull the data from the system, sends it to the cloud-based monitoring center, which converts those readings to smart drawings and graphs. What happened here was this roof was built in the winter in Minnesota, and moisture was frozen in the roof assembly. When that moisture thawed, it saturated down, hit the vapor barrier, set the system into alert, and it took 3 months to dry that vapor barrier out, and it occurred on 30% of the installed zones, and look where they all were. Transition, perimeter. No one would have known if that moisture was present if it had not been for a system. So, quick summary, you got 3 categories: ELD testing of the membrane, conductive mediums, which enables testing and roofing, and fully monitored systems. At this time, we are ready for questions, Mark.
Yep, and we've got just a few minutes left and got a couple of questions we haven't answered yet here. So I think we'll be able to wrap up right on time. First question is relating to the actual testing and who can do it. Is there a qualification process that needs to be followed to be able to actually do this type of detection?
Yeah, that's a great question. So, anybody can purchase ELD testing equipment and perform it. Any of the equipment manufacturers suggest training, but you cannot require it. Both ASTM standards do state that those testing should be trained. So okay. I would suggest if you're a spec writer, you should put in your specs, testing must be performed by a certified trained technician where they've been trained by the equipment manufacturer. That way you don't get somebody that just bought it off of eBay and never even trained on it.
Okay. The next question we got is are you aware of any type of precautionary or protective equipment that needs to be worn by the people actually doing the testing itself? I think that probably comes from, we're messing with water and electricity, and those things typically normally don't mix well.
Yeah, no, that's a great question. So for low voltage, The only requirement that I would say for low voltage is to wear waterproof, electrically insulating boots. It's low voltage, so it's less than 40 volts. You're not going to feel anything. No problems with this method or these two methods for low voltage. This only runs on 9 volts. Vector mapping is 40 volts. You don't feel any of that. It's not like sticking your tongue on a battery. High voltage, on the other hand, the equipment manufacturer suggests it should not be used by someone with a pacemaker. You should not use this method in a combustible area. There is an actual spark. It's high voltage but low amperage, so I don't think it can really kill anybody, but you don't want to touch that spark. It does hurt.
Yep. That makes sense.
Makes sense. Yeah, I saw one time we did a demo where someone had the high voltage equipment and just somebody pointed close to it and it sparked into their finger. So I've seen other people where you have 2 technicians and one of the technicians' boot was wet and the broom got too close to the boot, sparked into his foot.
Okay.
Yeah.
Next question we have, if the roof has hot rubberized roofing over a cementous coverboard insulation and a vapor retarder on the concrete deck, with the grid between the vapor retarder and the insulation, sounds like a conductive medium would be required above or below the cementous coverboard. Can you clarify on that?
Yes, it would have to go above it. So cementous coverboard might be semi-conductive, but not conductive enough. And so you don't want to expect your ELD testing is going to work on that cement board, because when you show up on site and you can't get a ground, testing cannot be done. So it's our opinion that if it's cement board, you do need a conductive medium, and the conductive medium always has to go on top of the non-conductive substrate, not below it. So in the case that you've given, you have to add in a conductive medium on top of the cement board directly under the membrane.
Okay, great. And I think our last question here, we've got one follow-up to that. Isn't hot rubberized asphalt conductive?
No, hot fluid waterproofing is non-conductive. Now, if it's saturated with water, covered with overburden over time, it could become semi-conductive. I have seen sometimes when the hot fluid kettle gets too hot, the fluid can carbonize, making it a little bit more conductive. But for the most part, hot fluid waterproofing is not conductive.
Okay. If lightning hits the roof, does it fry the grid or the monitoring system?
No, it shouldn't. So the conductive medium is grounded to the building. So any of your metallic objects are already grounded. The concrete, the soil, everything's already grounded. So that's not going to affect anything. The system is not connected to anything grounded. It's just, all it's doing is it's detecting moisture. So that would not affect it either.
And that might tie into the last question we've got here. Buildings that you mentioned, you had our research center there underground. Buildings that have highly technical operations within them that are, maybe they do a lot of lab testing and lab work that are very electrically sensitive areas. Any risk with this type of testing or ongoing detection messing with that or interfering with that, causing, because I know sometimes, you get too much power here and there, it starts going back and forth and you have all kinds of issues between different systems. Is there any risk with that?
Nope, no risk there. So like on the inverted system, this is only 9 volts in these specific grids. On the conventional system, it's just connected to power and data. So it's just a regular 120 volt quad receptacle. And so that's not going to affect anything. These are not electrifying the building at all. Same thing for the testing. High voltage, it's only sparking from the membrane to the substrate below. That spark really isn't traveling past that unless there's water saturation. But once it hits ground, it's done. It's only going to spark at the membrane surface. And then for low voltage, again, this is using up to 40 volts. The other is we're using up to 9 volts. That's not going to affect the building or anything at all.
Okay, great. All right. Well, I think that got us through all of our questions, and folks, we are right at the hour. Again, thank you, Shaun. Great topic. Very informative, very applicative, and especially with all the new technology we have in the world. This being able to be cloud-based and things of that nature. Very interesting topic, and thank you for your time. Folks on the call, again, thank you for being a member of CSINext. This does conclude our June chapter meeting for the month. At the end of this, you will receive an email survey, and on that you can select if you would like to receive a certificate attendance for self-reporting of your CEUs. If you do not receive that, please reach out to info@csinext.org and let us know, and we will be happy to get that taken care of for you. Again, I am Markov, Chapter President for CSINext, and thank you for joining us. Thank you for participating with us this year. We will start our new slate of programs in September. But that doesn't mean CSI and CSINext are taking the summer off. We're hard at work here getting everything ready for folks to start next year. So keep an eye out on the website over the summer. The president's blogs will continue. The member interaction and various topics will still be ongoing. So check us out at CSINext.org. And if you've got any questions, please feel free to reach out to us. Again, thanks for participating. Thanks for being a member, and everybody have a safe and enjoyable summer. Thanks, folks.
Thank you, everyone. Have a wonderful day.